Welcome to my Engineering and Science channel. This is the 200th video that I am presenting and analyzing in the circuit design playlist. For this occasion, I have prepared a special circuit, which is a unique one. It's an analog power raiser that receives two input signal V1 and V2 at the input of the circuit and then raises V1 to the power V2, reports a voltage at the output Vout that is equal to signal V1 raised to the power signal V2. I hope that you also find this unique circuit interesting. With that said, the idea is actually simple. So contrary to look of the circuit, it is just simply utilizing a trick that says, okay, if we are looking to compute, let's say, V out, in this analog computer, V out as V1 to the power V2, what if we actually say this is equal to exp of, or antilog of, let's say, natural log of v1 to the power v2. So basically, I didn't do anything. I just said, let's take a natural log and then reverse that by doing an inverse function, which is e to the power. And then if we do so, it becomes just exp of, and then natural log of v1 to the power v2 obviously is v2 is just v2 times natural log of v1. So the whole idea is now, what if I first compute in this analog computer, what if I first compute the natural log of V1 and then I do an analog multiplication, four quadrant, basically allowing positive and negative multiplications by multiplying V2 times ln V1. And then after that, I take antilog or raise exp of basically the result. So if I do that, I really get a signal V out, which is V1 raised to the power V2 with, of course, some baseline assumptions. So in this circuit, I'm going to show you that it's basically made of three subcircuits. The first one here that I'm highlighting at its output at this node is just computing the ln v1. So as you can see, v1 is entering this subcircuit here, as I highlighted, I mean this subcircuit. And this one is just computing for us ln v1 at this node. So natural log of v1. So that job is done. Now, the second subcircuit is multiplying v2 by ln v1. So that one, I'm going to show you that it is actually this subcircuit here, which is basically a four quadrant analog multiplier. And this one is taking care of receiving v2 as one input and receiving ln v1 as another input, and then multiplying both of them. And here at the very output, it's going to report for us v2. So at this node, it's reporting for us v2 times ln v1, basically the analog multiplication of the two inputs. And finally, from this node to the rest of the circuit, basically the third subcircuit is this one at the bottom, which is now receiving the analog product of the two inputs, v2 ln v1, and then computes the antilog, or basically e to the power, so that finally at the output v out would be effectively just v1 raised to the power v2. So that's the big picture of the operation of this circuit. I hope that this big picture helps with clarifying the circuit, because it looks busy, but it's actually a simple trick and idea, but it's a neat one. So with that said, what I'm going to do is I'm going to walk through these three subcircuits one by one, hopefully as quickly as I can. Just one heads up, the idea behind each subcircuit is getting rid of, because we are relying on basically a bunch of NPN transistors that should be matched, we are relying on their PN junction. So we are going to rely on Shockley, famous Shockley PN junction equation, which says voltage of base emitter of a PN junction that is on is just the threshold voltage, the terminal voltage, then natural log of the current of collector divided by, let's say, saturation current of the PN junction. So the saturation current and is heavily depending on temperature, is varying a lot with temperature and process. So the circuit is designed in each subcircuit so that we get rid of this saturation current as soon as possible. So that's one important step. And the other one is the thermal voltage, or VT, which is basically just KT over Q, in which K and Q are Boltzmann constants. So these are well-known constants, of course. Uh, it is linearly proportional to temperature in Kelvin. So we also need to, to a good extent, not perfectly, but to a good extent, get rid of that dependency. And that's the next step that basically I'm going to show. It's realized by the combination of this TEMCO and 50K potentiometer that I'm going to use specifically 40K out of the 50K range. The same here, this TEMCO or temperature compensating resistor, and combined with this 50K potentiometer, which I'm going to zoom into 40K range, is going to help us to get rid of again the dependency on VT as well. So in the sub-circuits, we not only get rid of the very varying and temperature dependent IS or saturation current, and we also try to remove the effect of temperature dependency because of VT to a large extent. So that's the big picture. I hope that at least this conversation is helpful before we get into quick details of computation. Okay, with that said, I'm gonna just turn off the video and then focus on the rest of circuit analysis. Thanks for watching in advance. Okay, so what is happening is now let's start focusing on the first subcircuit, which means the part that is computing the ln v1 from v1 that is coming in, as I mentioned. So let me clean this part so that we can just quickly go to the circuit analysis. And the big picture wise, as I said, I'm going to write it here so that as a reference we have it. Basically, we are saying V out, which is supposed to be proven is computing the analog exponentiation V1 to the power of V2 is simply the same as antilog or exp or e to the power. And then we have natural log of just V1 to the power of V2, which turns out to be V2 natural log times natural log of V1. And maybe I just write this clearly so that it's not forgotten. Okay, so as long as we can prove this, we are done. So to get to that point, we start with first subcircuit, this one. And I'm going to show that it's computing ln v1 at the output, which is at this node. This node here is the output of the circuit, basically OpAmp 1 and OpAmp 2. We are talking about output of Vout2, so output of OpAmp 2. Okay, so to achieve that, let's start with, again, the assumption that these two transistors, T1 and T2, the NPN bipolar junction transistors, we assume that they are matched transistors. They are on the same substrate, so they're very close to each other. They share the same process and temperature property. So what I can say is you can see that the base of the first one is 0, so we have 0 volt here. And then from the base, we have one base emitter drop, which is VBE1. And then we also have from the base of transistor T2, VB2, we have another base emitter drop, VBE2. So what I can say is, I can effectively say that VB2, I'm going to write it here. So VB2 is equal to, we have voltage of base emitter of transistor 2, and then we have minus voltage of base emitter of transistor 1. Now I'm going to use the Shockley p-n junction equation, which as a reference, I am going to again write it here. So Shockley p-n junction equation says voltage of base emitter is equal to the threshold, the terminal voltage Vt times natural log of the collector current divided by saturation current of the transistor, bipolar junction transistor. So in this case, just substituting using, let's say, equation 1. So this is Shockley p-n junction equation 1. I'm going to use that. And as a result, I'm going to get, let me shift this to a little bit left side so that there is enough space for further write up. Okay, good. So we have then voltage of base 2 is equal to Vt natural log of collector, or let's say the current of transistor 2, just let's put it that way, divide by the saturation current of transistor 2. and then minus voltage, the thermal voltage, and times ln I1, and then divide by saturation current of transistor 1. As I said, these two transistors are matched, so they have practically same VT and same saturation current. So that's the assumption. Now, because of the properties of logarithm, then I can just write VB2 is equal to VT natural log. Then this is the part that the two IS cancel out each other. We get rid of the dependency on IS, which is heavily temperature dependent, and we get this outcome. Now, I2 is, the current I2 is this one. I'm going to show on the, so the current I1 is this current, and the current I2 is this current, as I'm showing on the schematic here, close to the transistors T1 and T2. Now, these currents, obviously, since no current can go through the, let's say for the case of OpAmp 2, cannot go through the input terminal of OpAmp, it has infinite impedance, so let's say 0 microamp or 0 milliamp. And then because of the virtual short of OpAmp that are with proper feedback in the system, then we have ground as a positive terminal and virtual short forces to have the same voltage at negative, which is 0 volt, basically the negative terminal as virtual ground. So we have 0 volt here. Across resistor R, we have V1 and 0, and therefore I can just quickly write as a result that the current of transistor 2, I2, in numerator of this equation is simply V1 divided by R. The voltage across R divided by R. So V1 divided by R. And then the current of transistor 1, I1, is simply the same idea. This op-amp is enforcing virtual short, so 0 volt here and 0 volt here as well. All the current going this way as I1. And that current is simply I1 is simply just 1 volt across resistor R divided by resistor R. So I can just write 1 volt divided by R, and then the two resistor R cancel out each other. Just a general recommendation that resistors in this circuit are suggested to be low tolerance. Let's say if you can use thin film would be a good idea, but basically less than 1% variation, which is nothing strange, just it would help so that we increase the accuracy of the circuit. Okay, so what happens now is we get to the point that voltage of base of transistor 2 is just equal to, so I'm going to write it here. Let's continue here. So voltage of base of transistor 2 is equal to then VT and then natural log of V1 divided by 1 volt, which I'm not writing it. So there is 1 volt, basically in the argument inside the natural log is dimensionless because it is voltage divided by 1 volt. Now, what is VT here as we talked about it? It's just KT over Q, which can be also written as, given the value of, let's say, Boltzmann constant and the electron charge. Effectively, what happens is when we have a transistor, like these two guys that are matched, these two bipolar junction transistor, with PN junction at room temperature, we can write the VT or thermal voltage as roughly 25 millivolt. And then divide by 290, which is the in Kelvin, which is the room temperature, times the temperature. So basically when T, or the temperature of junction of PN junction, is at 290, then we get the 25 millivolt nominal VT for the PN junction of transistor, and then times ln V1. So you can see that we found, or basically this sub-circuit really computed the natural log of ln V1, but it's proportional to it, not exactly equal, because we have this dependency that you see. How do we get rid of this? That is the job of this last portion, combination of series of a TEMCO 1 kilo temperature compensating or TEMCO 1 kilo ohm resistor and a potentiometer 50K that I'm going to select, adjust the value of it so that I get something like 40K. So I'm going to make the adjustment. This potentiometer or variable resistor is giving me 40 kilo ohm. Okay, so when that is done, these transistors are low current, so they have a high beta or HFE. So HFE or beta or current gain of these transistors, or IC over IB, is pretty large, on the order of, say, easily much larger than 100, 200. So I'm talking about 400, 500. So the current of base is negligible compared to the current that is coming out of OpAmp going through the effective series of 40K and 1K, or the other way. Doesn't matter. So that current is much larger than the base current. Therefore, I'm going to neglect the base current of the T2, which is on the order of just microamp. So with that said, I am now going to just say that voltage at this node, which is Vout2, so remember this is Vout2. So I'm going to just say, therefore Vout2, okay, so therefore Vout2 is equal to, maybe I just write it here. So Vout2, or voltage at the output of the second op-amp at this node, which is the same node here, is equal to just the scale up of the series of 40K out of the 50K potentiometer and 1K Temco, temperature compensating resistor with nominal value 1K. I'm going to write the value of it as RT, so it would be 1 plus 40K, as I said, I set the 50K to 40K, and then divide by RT, which is the value of resistor of the Temco, or temperature compensating resistor. So that's the scale up from VB2. So VB2 is scaled up by this much to get to Vout2. From this node, we get to this node, basically, with a series of 50 and 1K. Now, substituting for VB2 from here, I get 1 plus 40K divided by RT times, and I have 25 millivolt divided by 290 times temperature natural log of V1. All right, so what's the next step here? The next step is just understanding what is Temco. So I'm showing you here a positive temperature coefficient PTC, temperature compensating resistor Temco, a nominal PT146. That's the component. There are a couple of options available. It's not just this one, but for this one as an example is a good one. The look of it is like this resistor, and it has a very small temperature compensating positive temperature compensation coefficient of 3500 ppm with 1%, let's say, variation. So with that, I am going to write, effectively that means RT is equal to, that's the meaning of it, is equal to 3500 divided by 10 to the 6, that's the meaning of 3500 ppm, and then we have the nominal value of it, which is 1 kilo ohm, and then times temperature. So as a result, it just RT becomes 3.5 temperature in Kelvin. So that's the beauty of the RT. It has positive dependency linearly with the value of the temperature. So then what is the outcome for this circuit then? With this, we can just substitute RT with this value. So as a result, we get just this outcome. So just remember that this T has to be temperature in Kelvin. So temperature in Kelvin. All right, so with that said, I'm going to just substitute for these values, and I'm going to get, using this equation, that Vout2 is equal to 1 plus 4D divided by 3.5 T. So I substituted for RT, and then we have 25 millivolt divided by 290 T ln V1. Okay, so the impact of this component is much larger. Remember that we have 40,000 in numerator and 3.5 T in denominator that in nominal temperature translate to 1,000. So it's we can practically, with a good approximation, just write this circuit as something like 41 divided by temperature. So 41 divided by 3.5, let's put it this way. I'm going to just write 41. The T effectively cancel out when we factor out the whole thing. The nice thing is the temperature of the RT is sort of tracing or following or canceling the effect of the temperature in numerator. So these T, the two T components from numerator denominator cancel out each other. Effectively, the whole equation becomes 41 times 25, that's 41K, 25 millivolt, and then we have 3.5 times 290 times ln V1. Of course, in this case, this is roughly 1, and therefore the Vout2, or the voltage at the output of OpAmp2, becomes roughly, practically speaking, just natural log of V1. That's exactly what we wanted. So that's the first subcircuit. The second one is easier one. This one had temperature dependency that I showed. We get rid of both IS, and also we get rid of, to a very good practical level, we got rid of the VT. Then next step is dealing with the second subcircuit, that is analog multiplier. So it's just multiplying the two input, which is V2 at one node here, and the ln V1, which is the second input to this analog multiplier. So let's see how it works. Okay, for that one is actually more straightforward. We don't have any further VT temperature compensation, just get rid of IS. So let's see how this is working. Take a look at again, for the value of resistors, we make the assumption they are properly selected. The good thing is, again, they are the same resistors. So if you're using, let's say, 10K or 5K, just make sure that it is a resistor that it has low variance, like 1% or less. My suggestion is, if possible, thin film resistors. Now, these 4 NPN bipolar junction transistor, or BJTs, they should be matched together. So they should be coming in the same process and on the same substrate and package, so that these 4 NPN transistors, they share the same process and junction and temperature properties. With that said, what I can say is, from the base of this one, which we can name it as, let's say, transistor T3, let's say T4, let's say T5, and T6. So what I can say is, from the base of T3, we have 0 volt. So 0 volt. From 0 volt, we go down by 1 VBE3. And then we get to the base of transistor T4, which then we get down by another VBE4 to a common collector. The same thing can be said about the VBE5 and then about the VBE6. So basically, for the second subcircuit, what I can say for the second subcircuit, the analog multiplication, what happens is, again, the second subcircuit of the analog computer here, effectively we are realizing an analog calculator that has 3 subcircuitry. So for the second one, we have basically this equation. We have voltage of base emitter from 0, the voltage of base emitter of 3, plus the voltage of base emitter 4 is equal to, so the sum of these two base emitters is the same as the sum of these two base emitter voltages. So we have is equal to voltage of base emitter 5 plus voltage of base emitter 6. Okay, I'm going to use again the equation 1, which is Shockley-P-N junction equation. So I am going to substitute the values. As a result, I have just VT ln current of transistor 3 divided by saturation current, plus VT current of transistor we have 4 divided by saturation current, equal to VT ln current of transistor 5 divided by saturation current, plus VT ln current of transistor 6 divided by saturation current. Again, these 4 transistors, as I said, they are matched transistors, so they have the same the thermal voltage, and they have the same saturation current IS. So with this written here, what I can do is, now I can just get rid of, let me just get rid of this redundant thing here. Okay, so with that said, I can just go ahead and effectively get rid of all the VTs on both sides of the equation. And also, when we have the log of the sum of logs, then we get the log of product of the arguments. So we have effectively just from this outcome, we get I3 times I4 divided by is squared. So divide by is squared equal to I5 times I6 divided by is squared, which, as I said, the transistors are matched, so we get rid of is squared from both sides, and therefore we get just I3, I4 equal to I5, I6. Now the job is just substituting these transistor currents. So I3 is just the sum of two currents. There is no current going through the input terminal of ideal op-amp because it has infinite impedance, and then the virtual ground and the let's say virtual short will be present. So as a result, here is we have 0 volt for positive terminal, so negative terminal is also 0 volt. So same idea, we have across this resistor 2R, we have a V2 voltage. So therefore, the current that is coming from that resistor this way, let's say the current that is coming this way is V2 divided by 2R. The same idea here. Here we have 0 volt, so that 0 volt is present here. And we have 10 volt, so basically the voltage drop across this resistor R is 10 volt. So the current that is coming is 10 divided by R. So 10 divided by R. So therefore, the I3 is the sum of V2 divided by 2R and 10 divided by R. So I'm going to just write it quickly here. Substituting I3. So this is what we got for the analog multiplier. And then substituting for I3, I'm going to get just V2 divided by 2R plus 10 volt divided by R. That's the I3 times for I4. If we look at the circuit, it is the current of collector of transistor T4. So as you can see, there are two things contributing at this node to current of collector of T4. One is the current that is coming this way, and then the other, the current that is coming this way. This current, same as before, so we have this op-amp here, op-amp number, let's say 4. So if we name the op-amps again, this is op-amp 3, op-amp 4, OpAmp 5, OpAmp 6. So we have up to this point dealt with 6 operational amplifiers. And then for the current, what we have is we have again 0 volt and 0 volt for the same reason, 0 volt here. So the voltage drop across this resistor R is just basically 10 volt. So this current is simply 10 divided by R. And this current here is again same idea. We have ln V1 on one side of 2R and we have 0 on the other side. So the voltage drop across this 2R is simply ln V1. Therefore, this current is ln V1 divided by 2R. So we have, I'm going to write it, ln V1 divided by 2R plus, and as I said, the other contributing factor is just 10 divided by R. So there is no other one that is contributing to this node. Therefore, I'm going to just write 10 divided by R equal to, so that's I4. Now the next part is I5. What is I5? I5 is actually the simplest one here, the collector current, because again, this op-amp 5 is properly biased with linear feedback, with negative feedback, and then virtual short is valid. We have 0 volt for positive terminal. For virtual short enforces virtual ground at negative, which means here we have 0 as well, and 0 volt here. No current flows this way to the input of op-amp. So we have effectively a voltage drop of 10 volt across this guy, and because of 10 volt here. And then the current that is coming is a simple computation, that is, so this current here, this current is just 10 volt divided by R. Okay, so I'm gonna just for I5 write 10 divided by R times I6. So this one here is just I5. I6 is this current, that is the most involved in the sense that we have a contribution coming this way, we have a contribution coming this way, and we have two contributions coming this way. One is effectively this current. Let me just write it right. So this current, that is across this resistor 2R, we have voltage V2. So because again, via this OpAmp number 6, the virtual short because of negative feedback and proper bias is there. So 0 volt at positive terminal reflected as virtual ground at negative terminal as well. And as a result, we have just the 0 volt here, which then means we have this contribution, which is V2 divided by 2R as a current. And also we have this contribution coming here, this one. For 2R here, that has ln V1 on one side of 2R and 0 on the other side. So we have ln V1 drop across that. So this current is just ln, or natural log of V1 divided by resistor 2R. So it will be 2R here. So I'm gonna make sure that these four components, meaning we have 10 divided by R, because of 10 volt across this R, and remember here is 0 volt. Now we also have this current that is coming from this side, and that current obviously is equal to, let's say if this node here is Vx or V out 6, let's say, that's easier. V out 6, the voltage of output of OpAmp 6, basically the output of the second subcircuit, which is supposed to operate as analog multiplier or analog computer. So we have across this 40R V out 6 minus 0. So this current is just simply V out 6 divided by 40R. Okay, so substituting these four currents, this one, this one, this one, this one. So the sum of these four currents, then I'm gonna get 10 divided by R plus V2 divided by 2R plus ln V1 divided by 2R plus V out 6 divided by 40R. So V out 6. Interesting. So this one is actually I6. If we take care of just simplifying the whole thing across this equation that I just wrote, and again making the assumption that, as I said, these four transistors are matched transistors, and the resistors that are selected, the R resistor, they are with good tolerance, like thin film or something less than 1%, then when we simplify this whole thing, when we simplify this interesting equation, the outcome will become effectively just V out 6 equal to V2 times ln V1. So it really does the job of just analog multiplication, because you just multiply the two inputs, which is V2 and ln V1 at the input of the subcircuit, which as I highlighted is this subcircuit, combination of 4 OpAmps, OpAmp 3, 4, 5, 6, and 4 NPN bipolar junction transistors connected this way to form 4-quadrant multiplier. In the use case of this circuit, we make the assumption that as shown on top, top of the page, we make the assumption that V1, the voltage or signal at the base of exponentiation or raising to power, is a positive voltage between 0 and 10 volt max. And we make the assumption that the absolute value of V2, the second input, is less than 10 volt. Of course, the resulting outcome V1 to the power of V2 should be less than 10 volt as well. So we should not forget about these practical assumptions, otherwise the output of circuit will saturate. Okay, so this is interesting outcome. And then finally, for the last subcircuit here, as I said, it's doing the anti-log or exponentiation. So it takes the V out 6 as input. So it takes the V out 6 as input. So I'm going to write it here. We have effectively we have effectively V2 times ln V1 as V out 6 input to the third subcircuit, which is this subcircuit here. And it receives that, and then it reports the V out exp of basically computing the antilog of the input V2 times ln V1, which is exactly what we wanted. Okay, so how does it work? Again, the idea behind the TEMCO or temperature compensating with PTC TEMCO, positive temperature coefficient of 3500 ppm, and the 50K potentiometer, which I'm going to again zoom in to use the value 40K roughly out of the 50K, is just getting rid of the dependency on VT. The combination of the matched two NPN transistors that I'm showing here that should be matched, these two ones get rid of the dependency on saturation current, similar to the previous subcircuit. So let's focus on the third one. I'm going to name these op-amps as op-amp 7 and 8. And I am going to name these transistors as, so we had up to T6. This is T7, and finally transistor T8. So from V2L and V1, we have just the inverting amplifier here, because positive terminal is grounded and negative terminal is connected like this. So it is well known for inverting amplifier that voltage at this node is simply minus RT, the 1K nominal. So actually the value is RT equal to nominal 1K RT. So let's write it clear. R TEMCO is nominal 1K, and then RT divided by 50K nominal, which is 40. I'm going to use the value 40K out of the 50K range. So it's minus RT divided by 40K out of the 50K, as I said, and times its input voltage, which is V out 6. So that's the voltage here. Let me change the colors because there is too much of a this color. So we have, let's say, this voltage at this node. Okay, so what is the next step then? The next step is from this node, which is voltage of base of transistor 7. How do we get to the output? Same idea. What I can write is from 0 volt here at the base of transistor T8, so we have 0 volt. I have a base emitter of T8, so there is the base emitter of T8, and I have a base emitter of T7. So what I can say is for this third subcircuit, so let me just move down. So for the third subcircuit, I can write voltage of, so I can write effectively, as you can see, let me just make sure you can see it. Yes. Okay, so I'm referring to the schematic. I can write the VBE7 minus VBE8 is equal to VB7. So VB7 is equal to voltage of base emitter of transistor NPN transistor T7 minus voltage of base emitter of NPN transistor T8. Substituting using the equation 1, the Shockley PN junction equation, is then VT, and again benefiting, so let me just write it, VT ln the current of transistor 7, the collector current divided by saturation current, minus VT, the current of transistor 8 divided by saturation current. And again, these two transistors, as I said, should be matched transistor on the same substrate, benefiting same process and temperature for the junction, PN junction, and therefore VT and VT are the same, IS and IS are the same. So therefore, I can just rewrite this whole thing. The property of subtraction for the two log will get rid of IS, which is the most troublesome component in terms of thermal variation. So VT ln, so I get voltage, thermal voltage, natural log, and again I7 over I8. So we got rid of IS. Now we need to substitute for I7 and I8 in numerator and denominator. So that's easy. So I'm going to then continue here. So therefore, voltage of base of transistor 7 is equal to, okay, so voltage of base of transistor 7 is equal to VT, which is as I mentioned before, so let's write it one time, VT ln, and then I7 is the current that is going this way, I7. And just one note, the cap here is just a 10 picofarad, or let's say 10 to 50 picofarad, depending on the type of op-amp and the speed of operation that you would like. Basically, it's a good idea to have this cap repeated everywhere that we have, let's say sort of a diode formation, or basically NPN transistor like this in the feedback loop of op-amp. That 10 picofarad cap just increase the stability of the circuit, make sure it is functional. So I'm not showing it the rest of the circuit just because it's too busy, but the presence of it here is just a reminder that it's a good idea to have that 10 to 50 picofarad cap just connected throughout the circuit. It might require a little bit of a trial and error depending on the op-amp that you have. So 10 to say 10 to 50 up to 100 picofarad might be a good idea. So with that said, that I7, again coming from this way, because of this op-amp in linear operation, we have 0 volt on for the positive terminal. Because of virtual short, we have virtual ground on the negative terminal, and therefore we have 0 volt here. It means that the current I7 is simply the current that is coming through resistor R, which is just 1 volt divided by resistor R, because there is only 1 volt drop across that resistor. So 1 volt divided by R. That's I7. What about the I8? The current I8, for the same reason, is just, again, we have 0 volt positive terminal of op-amp 8. Because of virtual short, we have 0 volt or virtual ground at negative terminal as well, which means the voltage drop across resistor R is simply V out. So I8 is just V out divided by R. So it's V out divided by R. Okay, so I'm gonna just substitute for I7 and I8. I7 is 1 volt divided by R, and I8 is V out divided by R. And remember, I mentioned that aside from the two NPN transistors being matched, so on the same substrate and matched transistors, then the other requirement is the resistors just being same type, and preferred is thin film resistor or something with less tolerance, less than 1% toward even less. So with that, we can get rid of R and R, and therefore what we get is a very nice outcome, is voltage of base of transistor 7, so basically the voltage here, is equal to VT and then ln 1 over V out, which I can of course write it using the property of logarithm. I can write it minus VT ln V out. But remember that voltage of base 7 is equal to just here is equal to, so it's connected via wire to the output of op-amp here. So let's say op-amp 9. And because of that, voltage of base 7 is just this value. So I'm gonna write it here. So that value is minus RT over 40K V out 6. We know, I'm gonna write it here. We know that voltage of base 7 is minus RT over 40K out of the 50K range times V out 6, which is, of course, based on previous outcome. V out 6 is the output of the second subcircuit, which was just simply V2 times ln V1. Okay, so I'm gonna just combine these things. So therefore, natural log of V out, let's put it this way. Therefore, minus VT ln V out is equal to minus RT over 40K V2 natural log of V1. Let me write it clean. V2 natural log of V1. So we are almost done. We just need one final push and we are done. And that push would be, of course, we get rid of these two negative sign that we have. So with that said, we're going to get just, and VT I'm going to substitute as we saw before. For VT, I am going to write, so it was 25 millivolt nominal value of the thermal voltage of PN junction at room temperature 290 Kelvin. So that's 290 Kelvin. And then times the temperature of the PN junction. So PN junction temperature of the transistor in Kelvin. So let me just write it clean. So temperature of PN junction of NPN transistor in Kelvin. Absolute value times natural log of V out is equal to minus is gone, so we got rid of the two minuses on the two side of the equation, and then we have RT as I said is 3.5 as I showed before, times the temperature of the PTC Temco resistor that should be thermally in conjunction with the transistors, divide by 40K, and times V2 natural log of V1. So we are almost done. What happens is, first, the best thing, we get rid of the 2T linear temperature dependency on the two side, basically one coming from the TEMCO contribution or temperature compensating resistor that you saw here, and one coming from the PN junction of these two matched NPN transistors. So they effectively cancel out each other. And then finally, what we get from this circuit is the 25 millivolt divided by 290 is the same as 3.5 divided by 40K. So they also cancel out each other. So these two guys also cancel out each other. They are the same. And as a result, then what I get is just the beautiful outcome. Natural log of V out is V2 ln V1. So I get ln V out is equal to V2 ln V1, which means, I'm going to just write it here, which means V out is e to the power or exp or antilog of V2 ln V1, which is the same thing as exp of ln V2 from the behind ln goes and become the power of V1, of course. That's the property of logarithm. So becomes exp of ln V1 to the power V2, which these two functions are inverse of each other, so they cancel out each other, and therefore we get V out at the output of this analog computer equal to V1 to the power V2 with the assumptions that I presented at the beginning of the circuit, meaning that we should assume these three simple sort of practical assumptions about the V1 and V2. And then at the output of the third subcircuit, we exactly get what was promised, which is V out is exp of V2 ln V1, or basically just V out is V1, signal V1 raised to the power signal V2. All right, so with this, I hope that this example, this sort of a unique circuit was an interesting example, and I hope that it is interesting to see how an exponentiation analog, let's say exponentiation raising signal to the power, can be realized using just analog circuit. I hope this was an interesting circuit analysis for you as well. Thanks for watching.